In this video, we're going to talk about critical paths as it's the next element in the networks unit. When we're talking about critical paths, it's this sequence of activities that cannot be delayed without affecting the overall completion time of the project. So critical paths are important in things like building. This is a set of guidelines that we're going to go by in order to work out the critical path of a network. And the things that are important is to work out the earliest starting time and the latest starting time of a particular event to take place. And we'll talk more about this in the example we're about to begin. So in this example, over here on the right-hand side, it tells us the 5 steps that we need to take each time we see a network like this if we're going to work out the critical path. The first one tells us to draw a box, split it into 2 next to each of the vertexes in the network, and then we actually put 2 when there are 2 edges leaving from a particular vertex. So if you think of the first vertex here, the start, we can see that A and B both leave, so we put A and B both here. When we're down here, once we've left B, when we get to this vertex, only E leaves from here. If we're up here on this vertex here, we can see that C and D both depart from that vertex. Over here, only F. Down here, we can see that G and H. So that's how we label each of the boxes. You'll notice I've already labeled the others. So that's the first step in each of them. Number 2 here says that activities that begin at the start of the project have an earliest starting time of 0. So we put 0 straight into the first 2 boxes as the earliest starting time. From here, we've got to follow the network. And we calculate the earliest starting time by working out the immediate predecessor and the duration of each of them. So when we get to this vertex here, we've been down at A, which has a duration of 8. So we write down 8 in both of these boxes. If we were to go down B, well, that would have taken us 9. Now, if we call this 9 days, for example, to complete that task. Well, once we get up here, we've got to keep completing the boxes. So if we go down C, it took 6 days plus the original 8. That takes us to 14. If we're going down D though, D was taking 7 days and we started at 8. So to get to G and to H, it was going to take 15 days. Another way to understand this is that G and H cannot begin until A and D have both been completed. And it took 15 days for both A and D to be completed. If we keep following the network, 9 plus 12 is 21. Up here, 14 plus 10 equals 24. When we get to this vertex here, you'll notice that there's actually 3 that are incoming to this vertex. When that happens, we have to work out the biggest one. So if I start from the bottom, we started at 21 and went up 6, that takes us to 27. If we go down H, we started at 15, went up 11, so that got us to 26. So 27 is bigger so far. But if we went down J, that took us from 24 all the way to 31. So 31 would have gone here. Now you'll notice that I actually did skip this one here as well. So when we were working out F, I calculated that being 24. If we went down G, that started at 15 and it also went up by 9, so that also landed on 24. Kind of skipped that earlier, but it's the same principle. When there's 2 edges that are coming into a vertex, you've got to work out the biggest one. In this case, it's actually the same. In this case down here, the answer to that one was 31. I'll tidy that one up a bit because that was the biggest. So we don't have to worry about 26 or 27. We then have to finish this by writing down the final 5, and that takes us to 36. You'll notice that it says the earliest starting time value at the finish of the project is the minimum time it will take to complete a particular project. So that in this case is 36. But we're not quite done yet. What we need to do is fill in these other boxes. In order to fill in the other boxes, we use a term called backward scanning. All that means is we actually start at the finish and we go backwards, following the same principles. I like to use a different coloured pen, and you're welcome to do that as well. So in the first box, we start at the very same number, 36. So the final number will also be the start of when we are backward scanning. That's what it says here. For part 2, it says to calculate the lowest starting time by subtracting the duration from the lowest starting time that we just had. So we would go 36 minus 5 takes us to 31. Now we can actually backward scan throughout the whole network. 31 minus 7 takes us to 24. 31 minus 6 takes us to 25. If we go down H, 31 minus 11 equals 20, and we put that next to H. Going down G, 24 minus 9 equals 15. Going down F, 24 minus 10 equals 14. And then I might start down here, 25 minus 12 takes us to 13. Up here, where we've got C and D both coming in, a bit like what we had at this vertex here, we've just got to calculate each on their own. So from going down C up here, it's 14 minus 6. That takes us to 8. And when we're at this situation here, though, where it's coming from a vertex that had 2, we always take the lowest number. So we could have chosen D coming from 15 or from 20. We choose the lowest one. In this case was 15. So we go 15 minus 7, that equals 8. To complete this network, we're going from 8 and we're going down 8, so that becomes 0 and 0. The next step that we have to do is actually highlight the critical path. The critical path is where, if we're going back to our original example, is a sequence of activities that cannot be delayed without affecting the overall completion of the project. So in this case, it's all of the numbers that are paired up and don't have a difference in the two numbers. And we can see that it's actually all the way along here. So it's D, it's also G, and it's down to K. It won't always have two paths. In this particular network, it obviously does. The final part to work out the answers to this network is to work out, well, what do these other ones represent? The difference in each of the edges with that don't align, so they've got a difference in their two earliest starting time and latest starting time, we call that the float time. So in this case, the float time for E is 4. The float time for I is 4. And the float time for H is 5. You might be asked a question saying, what is the biggest float time in the graph? And in this situation, the answer would be 5. So that's it. Took us a pretty long time to go through that example, but hopefully that makes some sense. There is one more part to it, and that's this final thing, and it's something called a dummy edge. A dummy edge is used when we create our own networks, and you'll have several questions that ask you to do this. So if you look at this particular network, what you'll notice if we were going through it is when we go up A, it goes up 8, which is here. C takes us to 9. If we were to go down B, that'd take us 6 plus another 2. That takes us to 8. A dummy is simply that a dummy adds up to 0, and it's basically just given when we add another edge, but it doesn't actually equal anything. So in this particular situation, we need to treat this edge here and this edge here the same. And when we're doing that using forward scanning, remember we have to choose the largest. So going from 6 plus 2 equals 8, or 9 plus 0 equals 9. So 9 becomes our earliest starting time. So that's how a dummy is used, and you will use these several times when designing your own networks.